Welcome back, chat. Today, we are going to jump in and continue our discussion about velocity and acceleration. We are looking at Chapter 2, Section 3. Before we get started, I want to have a huge shout out to my sponsor, Grammarly, which seemingly sponsors everything on YouTube these days. So there it is. Furthermore, big shout out to Zeke for joining my Patreon. Special content posted once a week. Appreciate you. Cool. So, this is everything that we did yesterday, summarized in as few words as possible. As we get going through stuff, there was one other question that we had, but I'll bring it back in. We need to consider two situations. We're obviously, go ahead. How much money you got? How much money is in your pocket?
He owes me the $10 that he owes me.
I never did.
Why do you think $10 is going to cover this? Yeah, go ahead. You're fine. Sign out. There's a sheet on the board back there, okay? Okay. Two options. I don't care which one we do first, because we're going to deal with acceleration and velocity stuff. Would you rather do the graph version first, or do you want to do the just mathy problems first? Graphs first? Okay. Right underneath it. That's fine. Cool. All right. So graph first. Now, as a reminder, and this is just a quick recall because we're going to look at two different types of graphs. If I have a position versus time graph, position versus time, and we can draw one. You don't have to because we've already drawn a lot of these. What sort of information can I get out of this graph? Position versus time. And if I draw one here, and let's just think about this for a second. If I had some position measured in meters and some time measured in seconds, and I were to look at this graph, that gives me some information of its position and time. Specifically, if you were to look at the slope of anywhere on that graph, anywhere, this point, for example, the rise is in what unit? If I said, here's a line at this point, and I'll point here so that anybody watching the video, but we're all here, so I should just be able to point. Anyway, if I said, hey, let's find the slope between these 2 points, and it's clearly whatever number that slope is, right? What's the y-axis, the scale?
Are we doing rise over one right now? Or
Sure. What unit, rather, is y-axis?
meters.
Meters over
Speed? Is that speed? Is it S? Oh, time.
time. So if we have a position versus time graph, which is what this is, the slope, and what's the letter we typically use for slope? Okay. Ooh, what?
M?
M in your algebra class, right? I'm just going to write the word slope. For this, the slope of a position versus time, the slope is the speed, or, depending on the direction, velocity. Okay, so just to make sure we have it, I will make this as clear as possible. Time and position. That's what we did in our last section. Position changes over time means you have some sort of movement or velocity. Okay, we're not talking about velocity though. What have we been talking about? Acceleration. So instead of being position changing over time, what's acceleration a change of? The change in velocity. Okay, so we see it's a rate of change, and we worded it similar to that. If we consider the following graph, let's look at this time instead of distance versus time graphs. We're going to consider a speed versus time graph. Now, when we deal with these, they give us a different meaning, but I want to make sure that we can see why this happens and how can we make use of it. So, let's say we have this lovely graph, and we'll get some real numbers for just a minute. I'm going to go all the way from 0 out to 9. And I have this lovely graph paper, so I can label this, no problem. You may not have the same benefit, but I'll give you a second. This is time along this axis, and we'll say that this is in seconds. And then, what's going to be the y-axis based on the label that we have for this header? Speed. Now, when we measure speed, and I'm making this as nice as possible so it's always positive, speed is measured how typically? Well, sure, fast or slow. Distance over time in the SI land, meters per second. Okay, now let's look at this. I'm going to just make up some random numbers, and I want to be able to make sense of what's going on. So I don't care how fast we're going. Meters per second, 10 is pretty quick. That's like Usain Bolt speeds. So let's say that this is 10 up here, which means that this would be 2 and 4 and 6 and 8. I just have some scales worked out. Speed versus time. I'm going to give you all a second to get your graphs set up. They don't have to be perfect, but they should be okay. So we have somebody who's starting here and they're not moving. And we're just going to build a graph together and we're going to make sure we can talk about it so we can write less, I hope. Okay. If I want them to go from 0 meters per second to 10, can they just magically jump in speed? No, because you have to accelerate through it, right? So if we're looking, hypothetically, we're making up this problem. How long does it take them to get up to 10 seconds?
2 seconds.
2 seconds. There it is. Okay. As we're looking at this, there it is, right? I can see it's happening. Okay. Now, let's say this person spent all this energy getting up to speed really fast, and all of a sudden they're just burnt. Now, they're not going to completely stop, but is it possible that over the next 3 or 4 seconds, at 5 seconds, maybe they slow down to 4 meters per second? Okay? And then let's say it stays at 4 until 8 seconds, and then they trip and fall, and they come down to no more speed there. Yeah, indeed. Now, this could be a realistic thing as somebody running. They take off from the blocks, they burn all their energy, they start slowing down, and then they just all of a sudden keep a constant speed, they trip and fall, and they stop. Like, that's a realistic thing that could happen. What I want us, and rather you, to do, but I'll help us get started with it, is using this graph, I want us to try to find a few different values. So from this graph, I want you to find, and we'll have a few different things. So I'm going to label these 1, 2, 3, 4, 5 because I'm going to use A, B, C otherwise, and I don't want to use A if it's acceleration. So first, I want us to find where they aren't speeding up or slowing down. There's another way that we could word that, and that's okay. Where on this graph are they not speeding up nor slowing down? Now, if you were paying really careful attention while we're making the graph, you probably already know the answer. If you were paying less attention while we're building the graph, you may not know the answer. I want you to, without just saying because Holloway said it was here, mathematically and graphically, talk with your neighbors, and let's see, we'll give you about 30 seconds, see if we can come up with an explanation for which of those time intervals they're no longer speeding up or slowing down. So, who has a good explanation for me?
Huh? I'm
Vincent, you think you might have it?
5
5
to 9 seconds.
to 9 seconds. Thumb, like, hands up, I agree with Vincent. Okay, how? I agree with you. How do you know that it's here that they aren't speeding up nor are they slowing down? So that, yes, I like the second thing you did. I just gave somebody else a hard time about answering that way, but you're absolutely right. You said something else afterward. This line is constant here, right? And the height that I'm at is my what? My speed. My speed isn't changing at all. My slope of this is 0. I can tell that there. So from, that was weird, from t equals what to what? 5 to 8 equals 5 seconds to t equals 8 seconds. Okay, easily identifiable on the graph. Okay, second thing. This one's going to seem like an easy question. I hope it is, but it might not be. Where is their speed changing the fastest? Okay, before you answer, I'm going to need a mathematical justification. Where is speed changing the fastest? Now, I could ask this question, where is their acceleration the largest? But it's a weird wording there. I want you to answer that question. Okay, I need mathy stuff. We have the mathematical ability to work this out, but I want you guys to make sure you can find it as well. I'll give you a minute. Talk with your neighbors. I need some algebra talk in here. Now, there's a little tiny bit of algebra. The slope on a position versus time graph, it gives you the speed or velocity, right? how fast or how far and how long. That's what it gives us there. When we look at this one, we get something very different out of it. Now, if I call these intervals, just so you know what I'm referring to, when I say from 0 to 2 for the interval, I'm asking you specifically on this part, 0 to 2, what changes occur on my graph. So I'm always going to refer from the x-axis just so we can look at it. Now, we're going to spend just a moment. There's something big going on out there that I should be aware of. Somebody getting yelled at? Okay. So I'm just going to work with the assumption that if somebody were getting jumped, you guys would like be a little bit less cavalier with it. I hope. Okay. All right. Okay. So check it out. I don't know, but we're doing this right now. I'm going to look at 4 different segments. That segment, can you tell me am I speeding up or slowing down? Speeding. Now, it's happening fairly fast. If I want to know exactly how fast, how many meters per second am I actually increasing, could we find the slope here?
5. Yes.
How'd you get 5?
Because 10 divided by 2.
Yeah, I rise 10 meters per second over 2 seconds. This section here has this, 5, whoa, too bold. 5 meters per second. Yeah, here's our Goldilocks. 5 meters per second. Meters per second squared is a better way to talk about that. I'm positive 5 at this point in time. Okay, could you find me the slope of this section right here? I go from 10 to where? Try again. 10 to 4, so I fall 6, and I run how many seconds?
3.
So -6, because I went downward, over 3 is what? -2. So we'll find this. On this section, -2 tells me something here. Does the fact that it's negative necessarily mean that I'm slowing down?
No.
Not always. However, this is my velocity or my speed. It's a positive value everywhere in here, and my acceleration is negative. Am I slowing down? Yes, that's that opposite sign. What's the slope here? Yo.
What's the square? Why is there a square?
Because if you take meters per second divided by seconds, we get to do the whoa or that whole thing, and we get meters per second squared. Yep, acceleration is always meters per second squared. Okay, Kevin, what's the slope here and why?
That'll be 0, wouldn't it?
I don't know. Would it? That sounded really snarky. It wasn't supposed to. Why? Work it out. I'm going to shove you in the right direction. How much do you rise between 5 and 8 seconds?
0.
Okay, divided by how much do you run?
0.
Careful. Along this x-axis or the t-axis, how many seconds pass when you don't rise at all?
Only 2.
I think it's 3, but either way we get the same thing. What's 0 divided by 3?
0.
0. So we have an acceleration of 0, and what's my unit?
Meters per second.
Squared. Okay, now here's the big piece, because depending on how well you drew your graph, it can be challenging to see whether this is steeper or not. Now obviously one's positive and one's negative, but we'll talk about that in a second. How much do I fall here?
2. Or never mind. Wait, never mind.
Careful, remember each of these ticks is 2, right? I fall 4 meters per second over how much time?
1 second.
So -4 meters per second squared. Okay. When we ask this question, the way that it's worded, I'm not trying to trick you, but I do want to check to make sure the language is there. Instead of saying, where is my acceleration the greatest? I think that it's guaranteed that 5 is greater than all these other numbers.
Yes.
Now, coincidentally, and I should have made this a little bit different, but that's okay. If I said, where's the speed changing the fastest? Do I care whether it's positive or negative?
No.
No, because I can speed up for speed to change the fastest, or I can slow down to have my speed changing. If, hypothetically, if I had seen something, and don't change your numbers, but if this had come out to be -6 meters per second squared instead, would your answer have changed?
Yes.
There, if that were -6, it's not. I'm using this as an example. Where is my speed changing the fastest?
6.
8 to 9 seconds, right, on that interval. Okay, using the graph, doable or super hard? So we're going to make one more comment here, much like the one we made before. On a position versus time graph, the slope is speed, or the velocity, however you want to think about it. On a speed versus time graph, what is the slope?
Speed.
No, that's not true.
Time?
When we work this out, all these units are just my slope being calculated. What do these units represent? Meters per second squared? What do we measure with meters per second squared?
Speed. Speed, no? Velocity? No, I can.
So don't guess. Okay, we have the velocity on the left. Yay or nay?
Wait, no.
How do you measure velocity? What units would it be?
Velocity is the
Ooh, careful.
It's
So wait here.
a roll over. No?
Check your notes real quick for me.
Wait.
Distance over time, like meters per second.
Oh, velocity with the other one?
This is velocity, right? So if I say what's the slope of a velocity versus time, does it make sense to say it's just velocity? I hope not. Yesterday we did a big thing where we did this whole, don't write it again. We did this meters per second.
Oh yeah.
And that comes out to this, right? What do you call the change in velocity? Not units. What do you actually just call how fast velocity changes? Oh my, acceleration. So we're going to try this again. The slope that we just calculated here, these are all accelerations, right? So the slope of a speed or velocity time graph, the slope, I'll go back and get rid of that one there. We'll write it nicer. And I'm going to write it in like big obnoxious color so that everybody like notices it. I don't know that we have any more obnoxious colors.
Purple.
Cool. All right, so it's going to look awful. Don't write it ugly. The slope.
Don't write it?
No, you should write it, but don't make it ugly like mine. Of a speed versus time graph is what? Good. Is acceleration. If only we had a shorthand for acceleration.
A
Thingy over it.
A.
quarter triangle.
Cool. I'll even write the word if you want it. I'm not going to have space. Don't write it obnoxiously large like this, but this is a really important idea. The slope. You can if you want to, like it's that important. Now, who do I want to give you problems just to try?
Yes.
Are you sure?
Wait. No, I was kidding.
Hmm.
We don't have time though. I don't know though.
I'm running out of time.
We could do one.
Wait, what is that?
I guess I watched that movie In Time. That was such a good movie.
Never heard of it. I think you made it up.
No, it's a good movie.
He's
In
a
Time.
liar.
All right. I really have never seen it.
What was
No.
the last part? Yeah, what's the last part?
I said
Acceleration.
Oh, I thought that said cool.
cool. Hey, QL.
Okay. For this, here's how we're going to proceed. Tomorrow in class, we are going to finish this section. We're going to jump right in with some practice problems doing this. We have a little tiny bit more because we're going to talk about two-dimensional motion in here. What it is looking like is that rather than having like a team test practice test tomorrow and then testing on Monday, you will have homework over the weekend. We will do a review day on Monday, and it looks like we're testing Tuesday. Cool. We still have like a minute and a half. So don't go wait by the door because it drives me crazy. Don't care if you get your stuff.